coming here, I want to...
Actually, we don't have distinction at bachelor levels.
Okay.
So, the specializations comes in the masters. So in the bachelors, they are having touch of each and every.
So are they students of physics or computer science?
So they are basically students of engineering college. They are in the electrical engineering or computational engineering related to that.
Mixed branches of engineering.
And biotech people also.
They take courses in physics like they do. You know quantum mechanics?
Yeah.
Good. All right. I'm going to be, this conference is a little bit of the work that put me on the map as doing physics with computation. Look at the price, $9 million of those dollars, right? And it took a whole room for this system. The total memory in this system was 32 megabytes. We could only access 16 out of those 32, 16 megabytes. We had disk storage and a laser printer and a drum plotter and tape drives where we had to store our programs. Now this was the disk storage. 2.7 megabytes per square inch, a total of 2.5 gigabytes, the size of a refrigerator, with a price of $100,000. And now you see what you have one of these things in your pocket, and it's about $20 for 2 terabytes. So the difference is enormous of what we were doing back then. This is the plotter that we had. This was a drum that rotated, and the pen sat still. The drum rotated, the pen moved up and down, but otherwise the drum, so you had X and Y. When I first used it, the only software, the only commands that I had in my hands to put in my Fortran program was pen up, pen down, move pen from point A to point B. That's all I had. So I had to write the code that would plot everything. Okay? And this was a vision for the future that I found somewhere, and I am not sure if it's real or a joke. Fortran, and it said where I found it, with teletype interface and the Fortran language, the computer will be easy to use, the computer of the future. Of course, now look at this thing about what we do with this thing, right? And Fortran was developed in the early 50s. By 1954, there was a vision that Fortran is going to be the programming language. Before that, they had to use assembly language, machine language, which I played with a little bit when I started. Anyway, that's not what we do anymore. And I will show you one slide now of what my theoretical tools are. Density functional theory is the modern way of solving Schrödinger's equation for the many electron problem in a solid or in a nanostructure, in a heterostructure, in any complex structure you want. And we do that by putting the whole problem into a supercell, what we call it, repeated periodically, and you have to be careful about how you do that so that you don't get interactions, strong interactions between supercells. The other thing is, if you don't know what they are, don't worry about them. The whole point is that we solve the quantum mechanical problem. And out of it we get total energies, which allow us to relax the atoms and figure out what atomic configurations are energetically preferred by minimizing the total energy, calculating forces, and so on. And we can calculate activation barriers for the atoms to move, because they can't just move, they have to overcome activation energies. And therefore, we can study defects and defect dynamics, which is a lot of what is going on in solids that affects operation of devices or controls the performance of devices and so on. And we can study optical spectra, vibrations, electrical transport, magnetic properties, and so on. We can calculate just about anything we want in order to address specific problems. Now, I'm going to focus my talk on two-dimensional materials on the nanoscale, and I want to tell you how it all started. We've always had materials, you just heard a few things that the previous speaker talked about two-dimensional materials, and I'm sure you heard a lot about them in the last 15 years. This is a structure of graphite where you have honeycomb structure of carbon atoms, and these are bonded very strongly on the plane and very weakly bonded between planes of atoms. The big discovery of Novosval and Geim in 2004 was with a very simple experiment. They were able to exfoliate one layer, and one layer had been known already by the name of graphene. So when you have one layer like that, you have a two-dimensional material, a true two-dimensional material, a single plane of atoms, even though they were two-dimensional with, like molybdenum disulfide, for example, has 3 planes of atoms, but they are all bonded together and then have layers of that. All right? People have been exfoliating layered materials for quite some time after that and studied a lot of them. There are literally hundreds of materials now that have been studied, and that became the era of two-dimensional materials, which has held great promise for new devices, new structures, and new applications. But we don't have an awful lot of them yet, but we still hope. I'm going to focus on materials that I and my collaborators have studied and discovered actually two-dimensional materials, new two-dimensional materials in the last few years, and we have done that with a combination of theory, which is done under my direction, and experiments, particularly scanning transmission electron microscopy, which gets amazing images of where the atoms lie. We have a three-dimensional material, and these are columns of atoms. This is a focused electron beam, and that little spot there is smaller than an angstrom. It's about half an angstrom. The distances between atoms are a few angstroms, 2 to 3, 3.5 angstroms. So the electrons that pass through between the columns don't do anything, but those that pass very near the atoms, very near the nuclei, are scattered in this angular detector, from which we form what are called Z-contrast images, with Z being the atomic number, and the intensity of the scattering is proportional to Z squared. It's a kind of Rutherford scattering, if you know about that. And I won't tell you about that. We won't need it very much today. It's a big microscope that wouldn't fit in this room, right? And costs, to get the latest version of these things, is about $4 to $5 million. Here is an image of graphene, a truly stunning image, taken by one of those microscopes. Every one of these bright spots is a carbon atom. You are looking, ladies and gentlemen, at individual carbon atoms. This is a photograph of them. The colors are arbitrary, we choose the colors. And this was taken by my friend and collaborator, Wu Zhu, while he was at Oak Ridge, and I was visiting there a day a week, and now he's in Beijing as a professor, and I visit there fairly often now, and we work together again. So this is not a single crystal of graphene. If you look through here, you'll see these big holes, and if you connect them, you get a grain boundary. Graphene is oriented in this fashion here and in a different direction up there, and they meet in this crazy grain boundary. But you see the astonishing behavior, the detail that you can get out of these images. This same microscope can be used also, because the electron beam is very powerful. For graphene, we use 60 kilovolts of energy for the electrons. They fly very fast, carry a lot of energy. You can use it for what you might call processing. And I will show you an example of that. This is my student, Junhao Lin. Over the last more than 10 years, I've been training students to do both experiments and theory. And this is one that has done theory and microscopy. And he used the electron beam. This is molybdenum disulfide. You saw that, some of that in the previous talk. So you see again the individual atoms. These are 3 layers of atoms there. You drill a small hole with using the electron beam. Then you drill it bigger, and then you drill a second hole, and you end up with a nanowire that here still looks fairly fat. And here it is now. I'm going to show it to you as a movie, how the electron beam is going to sculpt this nanowire and make it thinner, while at the same time the same beam is used to image it. Oops, wrong sign. Notice how robust it is under the electron beam. It gets yanked around, but it does not break. And it gets thinned as time goes on. And it gets kicked around. This was MOS2, and we changed the color here on purpose. This is molybdenum diselenide. It's a more beautiful video that I want to show you. So you see how reasonably fat is the wire. It's several atoms thick. And watch carefully what's going to happen this, and see how it gets knocked about by the electron beam. And now look, it peels off, and look how it gets kicked, and it does not break. These are 3 atoms thick. Okay? Now we've done, this is part of a set of papers where we combine theory and microscopy to study a lot of these things, and we predicted with theory that these nanowires are metallic, and then subsequently we found a way to verify that experimentally that they are metallic. But these are my demonstrations of what this microscope can do. This other microscope has also been known for a long time, scanning tunneling microscope. I wrote its name in red instead of green as the other one, remember the difference. This is a point that gets scanned again on the surface. Here is the point, here is the surface. And if you carry it along as you scan at the same height, then the current that goes through, tunneling current, varies with what's shown here is the electron density. So you get current there that varies with the topography of the surface. This is again on the far right, a picture of graphene taken in this fashion. Again, the colors are the choice of the experimenters. And many years ago, Dan Eichler at IBM was able to use the tip to push atoms around. These are krypton atoms on the substrate, and wrote the word IBM. Okay, I am going to give you a number of examples of how we discovered materials using a combination of theory and microscopy. The first one on palladium diselenide, done with my former postdoc, who here was to see if you can get monolayer PDSE2. This material is known to be layered, so you have these layers of this material, and if you go down to 3 layers, bilayer, monolayer, you would expect to get a monolayer of this, or peel it off, as others have done on other materials. This material had been studied by a number of theorists who found that the energy gap, this is an electronic property of the material that determines if you have a non-zero band gap, you have an insulator or a semiconductor. If there is no gap, then it's a metal. So a very small gap in the bulk material, and as you go to the monolayer, the band gap becomes 1.4. This is typical of 2-dimensional materials. As you thin them down, their properties change. But nobody was able to exfoliate this material and get a monolayer out of it. And my former student, Junhao, succeeded with this magical microscope, the scanning transmission electron microscope. Here's the material which he was able to thin with the STEM beam and go from the tri-layer to a bilayer and down to a monolayer. The problem arose as follows. You expect to have a monolayer of PDSE2. Well, if you look in the bilayer region, and you know how the atoms are arranged already because we knew the bulk structure and the structure of the monolayers, you could simulate what you expect for the STEM image. This is the simulation. This is exactly what he saw. So the bilayer was fine. But when he looked at the monolayer region, this should be the structure of the monolayer. And if you do the STEM simulation, this is the image that you should get. And instead, you got this, which did not correspond to any known 2-dimensional structure. So we got involved, and the question was, what is it? Working with Junhao, and doing theoretical calculations, we had the notion that maybe, because we knew that selenium atoms, and in general sulfur atoms in MOS2 or MOSE2, all of these chalcogenides, it's very easy to make selenium vacancies. And the electron beam can generate selenium vacancies. So the question, is it possible that we are losing a lot of selenium atoms? And therefore, if you start with a monolayer, which I show here schematically, and remove selenium atoms, could we change the stoichiometry maybe and go from PDSE2 to PDSE or PD2SE3? We looked and removed selenium atoms and tried the structure. We couldn't get anything that looked like what I simulated. So we tried harder and we said, what about if we start with 2 layers? How do we get a monolayer out of it? Well, we said we do want to remove selenium atoms. So we started removing selenium atoms here and used the computers and the total energy calculations to see what happens if we remove selenium atoms there and selenium atoms here. And we found out that they start approaching each other. They start interacting with each other stronger. And this is the result. The distance between the 2 layers was getting smaller and smaller and smaller as the concentration of vacancies increased. So we played with it for a while, and we saw what was going on, that whereas in the bilayer, the electron density looked like this, there is no electrons between the layers, so there's really no chemical bonding between the layers. It's just a very weak van der Waals interaction, as it's called. Never mind what it is, a weak interaction. But when we put selenium vacancies there, then the atoms are sort of more active, and they start pulling on one another, pulling the material, the 2 layers together, and getting a new layer out of it. And we worked with it for a while, and we finally got it, that 2 PDSE2 layers fuse into a PD2SE3 monolayer, and we got the structure to look like this as its lowest energy form. We simulated the STEM image, and we got this, which is exactly what was seen with the experiment. So we discovered a new material that comes from fusion or 2 monolayers, and here's the comparison. If you had tried to do a PDSE2 monolayer, you would get this structure and this STEM image, which you don't. You get PDSE3 from a fusion of 2 layers with this STEM image and this structure. And if you look sideways, this is what it looks. I told you it's 3 planes of atoms. It would be this, but it's actually this structure when you look at it from the 1, 0, 0 and from 0, 1, 0 direction. So this problem was finished. And we did a few other things about it that I'm not going to tell you now because I want to switch to another topic that is related to this. It's again have to do with PDSE2 and this material, the layered material now. And it's another form of 2-dimensional materials that we are going to make some devices out of. This was done almost in parallel, but a little bit somewhat when we were almost done with the previous, with collaborators at Oak Ridge. As I told you, I've been going to Oak Ridge National Laboratory for a day a week for 25 years now, and I've maintained students and postdocs there, and I am tapering it out now. My last postdoc finished in December. I still collaborate with people there. This was my theory postdoc there. This is the postdoc of Kai Shao and David Cohegan, who did most of the experimental work in synthesizing materials. And she did the microscopy under the direction of Matthew Chisholm. This is the paper that came out last year. What the point was here is that the palladium-selenium system is very complex. This is a phase diagram as a function of the percentage, the weight percentage of selenium. And this is temperature. If you look down here, the PDSE2 is in this regime, right, of half and half, and or 2 seleniums to one palladium. And if you remove selenium atoms and come this way, you can get PDSE, you can get the strange stereometry PD17SE615, and then again PD2, whatever it is, SE4. All of these are metals over here. The PDSE2 is the only one that is layered. This other, the PD17, 15, if you start removing selenium atoms from PDSE2 and come over here, these are all metals. So the idea here was to make a contact. If you start with this layered material and remove selenium atoms, the question is what you're going to get. And they did the experiment where they bombarded with argon plasma, which would generate selenium vacancies, and they found that it gets converted from layered material into the non-layered metallic PD17 Se15. Kind of strange geometry. But now it's a solid material, not layered, and it's a metal. The usefulness, okay, let me show you this. This is the images that you get from the layered material, PDSE2, and this is the bulk form of PDSE2, 1715. And here's an interface between I can't even see from here, the layered material and the bulk material. And the interface was very important. The purpose of this was to make a device by making good contacts. Contacts to two-dimensional materials have always been a problem because the two-dimensional materials are layered. They don't like to interact with anything. They don't interact among themselves as layers, and then to put a metal, a gold contact in it, doesn't stick very well. But by doing this process with the ion bombardment, you start with the layered material, you put a mask on it, then you do the argon plasma there and there, and you get this to be incorporated in the structure with an excellent contact. We made a device, and here is the properties of the device, that the mobility of the electrons in the 2D, in the layered material, so here is the layered material with a titanium gold contact, or with a contact including this PD1715. Okay. The electronic structure is very different. Here you have a Schottky barrier, here you have an ohmic contact. Here is the mobility of this structure, which you could do with gold contact, and it's down here. When you do this, you get the mobility to go up by more than an order of magnitude. So we looked at it to find out how does this transformation occur, and why do you stop at PD1715 and don't keep going and lose more selenium? And we looked at how you can remove selenium atoms to get from the PDSE2 layer to the bulk PD1715. And we tried a lot of different things, and we calculated the total energy difference, the cost of energy to remove this, and therefore you are going to remove the ones that cost the smallest amount of energy. That's what the beam will do. And we found, I won't walk you through this, but my postdoc spent a lot of time figuring it out and showing how by removing these pairs of silicon atoms, you can go continuously to PDSE, and calculated the energy cost to do that. And then we found out that once you go to PDSE, you can remove a few more silicon atoms with a minimal energy cost. And then after that, it's very expensive to remove more selenium atoms. So the thing gets stuck at the strange geometry of PD17 Se15, and allows you to make those devices that are better than anything else that anybody made with two-dimensional materials. My next example is to use the microscope that I labeled with red ink. That's this microscope. I'm going to give you a few examples. And this work was done using a scanning tunneling microscope with my collaborators in Beijing, China, whom I visit every few months and work with him on several projects, participating from the concept of the experiments, theory, and analysis. The group is led by Hong Jun-gao, an academician in Beijing. His second in command is Xishuan Du, who does theoretical work as well. And these are the senior experimentalists that were heavily involved in these papers. Yu Yang was a student from that group, that spent several years with me as a postdoc. And Wu Zhu is the STEM microscopist who is now also in Beijing, and we needed him in this project. I'll show you how. Now it's about patterning of two-dimensional materials, which had been done by several people by lithographic techniques. Instead of having a homogeneous two-dimensional material, by using masks and resists and so on with lithography, you could do patterns like this, but on the scale of microns. And the idea there is that if you have a patterning, then you could do different things for the, let's say, the black region versus the red region. You could put different molecules on it to different functionality and so on. And we did intrinsic patterning. The first thing that we did, that's a misspelling, that's a PT, platinum diselenide. That's the first paper that we published, no patterning, but we did this by taking platinum substrate, and those substrates are very expensive, by the way. Platinum is extremely expensive, like $10,000 for a square centimeter. And we did something simple, actually. Evaporated selenium in the vacuum chamber and cooked it a little bit, annealed it, which is the analogy of oxidation. If you have oxygen around and heat, you form an oxide. And we succeeded, in a sense, to do selenization of platinum. And we got platinum diselenide, but it took us a while to figure out what we had. This is what we got, STM image. Here is at the high resolution. We formed the model, and we thought we had for a while, but we were not sure among different models whether we had platinum selenide or merely a layer of selenium. We needed to confirm that. And that's when we went to the STEM microscope and looked at the thing sideways to see what we had. And this is what we got. This was quite an exercise. I took a sample with me from Beijing and took it to Oak Ridge. That didn't work, and we had to take a different sample to Tokyo to get it done. And it was all guided by my friend and collaborator, Steve Pennycook, the world-class microscopist who's now in Singapore. He used to be at Oak Ridge. And we convinced ourselves that we have exactly this thing, which is platinum diselenide. We published this paper, hey, new material. Nobody had ever done this. But then we did something more clever. With magic, as my friends in Beijing know how to do really magic. If you start with homogeneous PTSE2, which is what we have, you can see how beautiful it is, on the scale of nanometers. This is why it's nanostructural. And anneal it at 400, and you might say, why 400? Because they played for a while and tried different temperatures and got interesting things until they zeroed in on a certain annealing process which gave them these beautiful triangles. And the triangles were either the 1T structure, which is the structure of this thing, or the 1H structure. The atoms are arranged slightly differently, but the 1H form is known, but it's not stable at room temperature. There are other materials in which the 1H structure is the stable one. So it's a known structure, but here we succeeded in doing this, and we understood what's going on. When you anneal it, you lose selenium atoms. Back to the same theme, that selenium atoms come out, and we found out that if you generate things, you actually gain energy to go from this. If we these are done, they come off by heat, the 400 degrees. The calculation tells us that you gain energy if you arrange these vacancies in triangles. And once you have the triangles, so the vacancies go to the boundaries, and then we found out when you confine the 1T structure in the triangle, it's energetically preferred to form a 1H structure. So we understand what's going on. And this thing is reversible. As you see here, you can go back and add selenium, anneal it at the lower temperature, and you go from this to this. This was all confirmed with a variety of experiments that I'm not going to show you. And I'm going to go to the fact that our idea was, can we get a pattern material and then find molecules that absorb preferably on the one or the other place? And in this case, we tried and calculated all kinds of molecules, and we found they always prefer to go, I believe, on the binding energy is larger on the 1H. They didn't want to go on 1T. So we tried something else, and this was work that was done in parallel on copper selenide. We selenized copper, and we got copper selenide. And here, the patterning again was intrinsic, but it was little holes. You can see the big picture here, and you can see a boundary between triangles that point up and triangles that point down. Here's the triangles that point down, here's the triangles that point up, and the boundary in the middle. Here is the image of one of the holes. You can see the resolution of the 1 nanometer scale. And again, we constructed models of this, and we demonstrated that when you try to remove selenium atoms to make a hole, the energetically preferred case is when you do 7, you remove both copper and selenium, you remove 13 atoms, and that's exactly the hole that you see in the experiments. All the others are energetically higher. And then we looked at putting different molecules. We put just iron atoms, evaporated, and they all went and fell in the holes and made these W figures. And then we put some big molecules, like this is iron phthalocyanine. It's an iron molecule surrounded by these these carbon structures. And they are too big to go in the holes, so they sat outside. So we succeeded in getting selective molecules. The promise here is that you could have molecules that do sensing and molecules that do catalysis or other things like that. We succeeded in patterning other materials as well. This is selenizing vanadium. We got a completely different form. Here is the homogeneous material. And this one, when you anneal it at 350 and you lose some selenium, you lose the selenium from chains of atoms, and you get chains every 4, things like that. We studied them in detail, and then to go quickly to the functionalization, we decided to try platinum atoms on this to see if we could get these platinum atoms to do catalysis. Platinum is one of the best catalysts for a lot of things, and we are interested in particular in the hydrogen evolution when you break water molecules and you want to get hydrogen out. Platinum is the best catalyst, and it's expensive to have surface of platinum macroscopic quantities. So lots of people try to find alternatives, and we tried isolated atoms. And indeed they go in an isolated fashion, always in these channels. Here is a case, and then they go like that, or like this, or like that. And experimentally, they do exactly what we said they do. They go in those stripes and sit in there. Here's the details. And here, the thing we did, what happened to my slide? I don't have it. I lost it. It's a slide that shows you the calculations that monatomic platinum on this material, we calculated its catalytic activity, and we found out it's very close, extremely close to that of platinum surface. All right? So I will leave that at that. I just wrote these words here. And the last thing on this patterning is silver selenide. And here it goes Ag5 Sc2. And it gives you these amazing triangles where we studied the grain boundary. It looks like that, the boundaries. But look at all these offsets here. All right? And this is just a one-slide show. I tell you, we succeeded here to co-adsorb 2 different molecules. I think one is pentacene and the other I don't remember. And we've got molecular corrals. You can see here, if you look over here, is that one molecule goes on the boundaries and the other goes inside. So we have the ones inside there being a corral, which is something that lots of people try to make corrals in different ways. And this is the first one. This we haven't published yet. The paper is being written now. The others have been published. And how am I doing with time? I ran out of time.
So you have about 5 minutes.
Another?
Yeah.
Okay. I have only one more thing to tell you. Monolayer amorphous carbon. This was done by my friend Barbaros Ozelmaz in Singapore. Chitad was his postdoc that did most of the good work. Microscopy was done again by Junho while he was still a postdoc at Kazusu Enaga's group in Tokyo. Now he's a professor at the university in China, and I was supposed to visit him, and then the virus came about. I don't know when I'm going to go back to China. Yunpeng was a postdoc at Vanderbilt with me and did the theory. Barbaros is an amazing materials synthesis that synthesized for the first time ever monolayer amorphous carbon. And we worked together for a long time to do they did the additional experiments. Yunpeng and I did the simulations. Junhao took pictures to really understand both its properties and what the messages from that are. Tell you a history of amorphous materials. I worked on amorphous materials in the 1980s, and for decades, the nature of amorphous materials was debated between a 1932 paper by this fellow here, Zachariasen, who started his that seminal paper in 1932 with the words, "It must be frankly admitted that we know practically nothing about the atomic arrangement in glasses." It was true, and he made the suggestion, essentially, that if we do a diagram in 2 dimensions, he didn't know about 2-dimensional materials then, but it was a schematic to demonstrate his ideas, is that silicon dioxide, for example, is a 3-dimensional material, glassy material, where you have rings like that in 3 dimensions. If you think of the red balls as oxygens and the blue balls as silicon, silicon dioxide is like that, and it has in 3 dimensions 5-member rings and 7-member rings and 6-member rings, and he said this would be the continuous random network model for amorphous materials. There was a competitor that goes back to 1835 in some obscure paper, but then it was taken up by the Soviets, and earlier, before Zachariasen didn't know about these things. This was buried in somewhere, and Lebedev was a famous Russian scientist. There's an institute in Moscow called the Lebedev Institute, and he made a suggestion, essentially, that amorphous materials are really microcrystallites buried in messy material. The messy material, you might think of it now as continuous random network. And the debate was going on in the 50s and the 60s and the 70s and the 80s. I started playing with these materials. That are they continuous random networks or are they microcrystallites? The available evidence was in the favor of continuous random networks. But more recently, with some new techniques, this fluctuation electron microscopy, I won't explain it. All I will tell you is that you measure certain things, and then you try to simulate them. You simulate what you measure by looking at a continuous random network. This was silicon, which sounds like silicon dioxide has these ring structures, and see which one can simulate the curves better, the microcrystallite model or the continuous random network. And these kinds of experiments kept coming in favor. As you can see, this is in the 2000s. It started in 1996, but they all came in favor of the microcrystalline model, which was not the orthodox point of view at the time. By the end of the century, the Soviet Union didn't exist anymore, so the dogma of the microcrystallites went away, and everybody believed in continuous random networks. This is where we were when I got my hands on Barbaros's monolayer graphene, and we analyzed it from this perspective, and here's an image of what is known as nanocrystalline graphene. You can see that these are grain boundaries, like I showed you in that very first image that I showed you, right? This is graphene pointing in one direction, graphene pointing in a different direction. This is nanocrystalline graphene, as opposed to single crystal, which is just like that. This is Barbaros's monolayer amorphous carbon, and you can see that this is really and truly This is atomic scale imaging, and we colorized it to see that this is a continuous random network going all over the place, and they are unambiguous microcrystallites, or nanocrystallites in this case, in there. And this paper was accepted by Nature. It was published just a few weeks ago, right? And here is a model of the nanocrystallites with the arrows pointing in different directions, which is important. And we made models, and we studied its properties, and we learned a lot of things about this, this particular material, and we are still working on it. It is, there. Here is a, the electronic structure of it. Those of you who know about the density of states in graphene, it comes down like that. And this is the Dirac point, and it's an excellent conductor. But when you go into this material, you find these states that sit around the Dirac point and ruin its conductivity, because the wave functions of this material, of these states, are not continuous, but they are distributed randomly in this model where you have all these nanocrystallites. Experimentally, the optical gap was measured at 2 eV, and I don't remember what else I have here. And that's my my story, and I think I finished on good time. And the point of my last slide is that microscopy, STEM or STM, and even other